Alright, normally on a problem like these, like the parakeets, or some of the other ones I'm going to show you that are dihybrid crosses, on a test, it's much more likely that I will ask you for the chances of just one type of offspring, not for the chances of all the types of offspring, because it's much more time-consuming, obviously, to look at every single possible combination, and obviously your time is limited on a test, and there's other things that I want to test you on. So for the short answer, for example, you will have a question kind of like this, where you have a dihybrid cross of some kind, but I'm just going to ask you, what are the chances of purple flowers or yellow parakeets? I won't ask you what are all the possible outcomes that could happen. So first thing I want to show you, when you're doing a problem like this, it's really important that you sort out the possibilities for each color. So in the parakeets, they tell you, for example, that big B dash, big Y dash is green. You need to be familiar, I know I've mentioned it before, but I'm just going to reiterate it, with that dash. The dash means that there is a second letter, because some people were thinking the dash just meant that they only carried one letter. They're always going to carry two. The dash just tells you that it doesn't matter if it's homozygous or heterozygous. That's what the dash means. So as long as there's at least one big B and one big Y, you're going to have a green parakeet. And then yellow is the little b's with a capital Y, anything, and then blue is capital B's with little y's, and then there's only one code for white, which is little b, little b, little y, little y.
So if you're crossing that, how would you fill in those dashes?
So that's what we're going to do right now. So the first question says that you're crossing a green parakeet that had a parent that was white with a white parakeet. So you already know white, because there's only one combination. So you know that you're crossing it with this. What you don't know is, you know that it's green, so it has to have a capital B and a capital Y. How do you figure out the second letters? This is why they told you that it had a parent that was white. And they're always going to have to give you enough information to figure that out. So if they had a parent that was white, remember that the only code for white is this. So that would have to mean that they're big B, big Y, little y, because they would have received a little b and a little y from that parent. And they will always have to give you enough information to fill that in.
So if it was green, then it would just be capitalized.
Yes. So this particular question, like I said, is a little more in-depth, because I ask you for all the possible genotypes and phenotypes. So if you cross your B's, I'm going to do it using the product rule, even though technically you only need a 4-box square to do this problem. It's a weird 4 boxes. It's a wide 4 boxes. But I think the product rule is the way to go for all of these. So my chance of, let's just write out all of our possibilities. So it's a 1/2 chance of big B, little b, a 1/2 of little b, a 1/2 big Y, little y, and a 1/2 of little y, little y. So that's our breakdown. Now, again, this is a little time consuming. Chance of green parakeet offspring, big B, anything, big Y, anything, would be a 1/2 chance of big B times a 1/2 chance of a capital Y. So it's a 1/4 chance of green offspring. Does that make sense? To get our chances of yellow offspring, and again, I wouldn't ask you on a test to do all of this, the code for yellow is little b's with at least one capital Y. So the chances of little b is 1/2, and the chance of having a capital Y is also 1/2, so you're going to get 1/4 again. And for this particular problem, you actually get a 1/4 chance of everything. That's not always going to be the case. I think I gave you 2 different problems on this particular worksheet, and it was 1/4 for both of the problems. To be blue, it was capital B's with little y's. Again, 1/2 chance of capital B, and a 1/2 chance of little y, so that's going to be a 1/4. And then to be white, little, it's a 1/2 chance of little b, and a 1/2 chance of little y, so yet again, 1/4.
Oh, so you use the Punnett squares to determine the likely of when you ask the different when you say
yeah. Exactly. So if you look at the second one, this time they told you exactly the genotypes of the parents, so you don't have to figure that out. They want to know what are the chances of this parent and this parent offspring. So we already said, we know that to be green, they just need to have at least one capital B and at least one capital Y. All right, so I'm going to cross my B's first and then cross my Y's. All right, what are the chances of having a capital B in the offspring? 1/2 again. So we're looking for the chances of this code. So 1/2 chance, and the chances of a capital Y also 1/2. So yet again, this particular code is 1/4. All right, and I'll show you a second problem where you don't get 1/4 of each, because we keep getting 1/4, and I don't want you to think, oh, see, it always ends up being that, because that's not the case. You will definitely have a short answer question, something like number 7, and I believe there's a multiple choice similar to it too, where I either will give you how many combinations are there, or what are the chances of a particular combination. So I know that everybody should know how to do this by now, but I'm going to go ahead and scroll up and do this one really quick. So how do we get the number of possible combinations? Right, it's just going to be 2 to the n, where n is, how do we get n? Yeah, I just went to a different sheet. There we go. Okay, so 2 to the n, where n is the number of heterozygous. And so if we look at this one, there are 1, 2, 3 heterozygous pairs. So 2 to the 3rd, there are 8 possibilities. For then, what are the chances? Usually, quite honestly, you're probably going to get the same number you got here, but 1 over that number. If it's possible, because basically there's 8 possibilities. So probably the chances of this are going to be, this is probably 1 of those 8 possibilities. But if you want to be certain, because like this one is a trick question. This one is 0. Why is this not possible? Right. So when you start it out, it works. You're like, okay, the chances of it giving a little a, it has big and little, 1/2. The chance of a little b is 1 because it only carries little b. The chance of c's is 1/2. The chance of d's, though, is 0 because it's big D, big D. And immediately, once one of the things is not possible, the whole answer is just 0. It's not possible. And that is an answer you could get. Yes.
What are the chances of big A, little b, big C, big D, big E, 1A?
Oh, this one? Okay, so I'll show you. So the chances of big A, I've kind of made a mess of this. Let me erase that. Okay, so the chances of big A are 1/2, right? The chance of little b is just 1 because it's only little b's. The chance of big C is 1/2. The chance of big D is 1. And the chance of big E, again, is 1/2. And when you multiply that, 2 times 2 times 2 is 8. So that's how you get 1/8. And like I said, normally you're probably going to get 1 over whatever that number is. It's kind of a trick, and you could double check yourself. Yeah. Well, if there were 2 parents and you were asked for the chances, I wouldn't do it this way because you could screw that up if it's heterozygous. So I don't know if I have one like that on here. I don't think I do. But I know what you're talking about. If I have like AA, BB, CC crossed with whatever, what are the chances of little, whatever? I would do 3 separate Punnett squares and multiply those chances. I would not do it this way. Technically, if they're all homozygous, it'll probably work to do it this way. But if any of them are heterozygous, you may get the wrong answer because, so I wouldn't recommend doing it that way. Tommy, you have a question? Yes. Natalie. Tommy, what was your question? Oh, yeah. This table, you won't have a table like this to fill out on the test. However, this is a really good practice for understanding how to work backwards. The reason I put this on here is so that you would get practice with those kind of genetics problems where they tell you the offspring and ask you about the parents. And the word progeny, by the way, just means offspring. It's a very common word you may see used instead of child or offspring. Progeny is a word. First thing you want to do, you want to look at what trait is recessive. Recessive is going to help you a lot on almost every genetics cross. So in this case, they tell you that yellow is dominant to green. So you already know every single one of these parents that's green has to be little y, little y. So that's the first thing I would do, is I would fill in, so this has to be little y, this has to be little y times little y, and this has to be little y, little y. Obviously, if a parent is yellow, they could either be homozygous or heterozygous. So when it comes to those, that's where the offspring come in. This is your key. The offspring showing the recessive trait. Because you know if they show the recessive trait, they have to be little y, which means they had to get a little y from each parent. So even though this parent is yellow, it has to be big Y, little y, because they had some green offspring. How about our second cross? Both parents are yellow. Right, but they both have to be big Y, little y, because that's the only way they would have had green offspring. Now when we look at this one, yellow crossed with green, all the offspring come out yellow. What's this parent? Now we know this is big Y, big Y. Is it possible it's big Y, little y, and had all yellow offspring? I guess yes. Theoretically, it could be possible. But it would be so unlikely. They would never expect you. They're wanting you to say, if all of them come out showing the dominant trait, just like in a test cross, you're going to assume that means they're homozygous. Honestly, on the last one, there's more than one correct answer. Both parents are yellow, and at least one parent has to be homozygous because they didn't have any green offspring. But technically, I would have accepted either answer. I'm just going to put a big Y with a dash because the second parent could be big Y, or big Y, little y. And no, you didn't have to put a dash. But you don't know for sure. Because as long as one parent's homozygous, all the offspring would have come out yellow. So you don't know for sure. Every other one of those is only one correct answer, though. So if you were able to do all of these, then you're in very good shape with understanding how to work backwards in a genetics problem. Yeah?
So if on the test there's something similar where you could have either answer, would you put those or one or what would you put? Doesn't matter?
I mean, probably it would only be multiple choice because I don't have a short answer like that. But if it was multiple choice, it would probably have options like which of these is possible, and then you would check all the ones that were possible. Yes? Because this one had a green parent. So you know this one has to be little y times big Y, big Y. But in the other case, they were both yellow. All right, let me do this chinchilla one. I can tell you there's nothing as challenging as that one on the test. But the idea with this chinchilla gene is this is a gene in rabbits, in the coat color of rabbits. This was supposed to print out with greater than symbols. This is a kind of gene. It's one gene. That's why they're using one letter. But it has 4 alleles. A lot of people are still shaky on what an allele is. An allele is a form of a gene. In this case, there are 4. There's C, C with a CH, C with an H, and C with an A. And again, this is harder than anything I would give you on a test. But this one happens to show like a hierarchy, meaning that like C is dominant to all the other ones. So you'll notice in the table here that if they have a C, they automatically come out full color, no matter what the second letter is. And the only way they can be albino, because that's like the most recessive, is they have to be C little a, C little a. Because if their other copy is any of the others, they'll show the other color and not albino. All right, so this is probably the harder problem, because C is actually pretty easy. So in this problem, here's what you're going to do. A full color rabbit. If you look at full color, you'll notice they have to be C something. So you automatically know the first letter. It's crossed with a light gray. If you look at light gray has to have C, CH. The clue here to figuring out what the other letter is the recessive. They have some albino offspring. If the only code for albino is this, now you know what must the second letter be for both parents. Has to be C little a, because that's the only way they could have made an albino offspring. So to attack these, my suggestion, look at what color they are, write in what you know has to be there, and then to figure out the letter you don't know, look at the offspring and work backwards. And that should be able to do it. The second one is actually really easy. It looks like it's a hard problem, but in this one, literally you just do a Punnett square. C, CH, 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 CA, and then you just fill it in and look up what colors they would be. Like this one, C, CH, CH, would be light gray. And if you fill it in, I believe you get half light gray and